Okay.
Yeah. Professor Buffedo, the time's up. Shall we start?
Yes. I mean, let
Okay.
me. So I guess I can share my screen. Let me share my screen.
1 second. Before that, I will give a short introduction. Is that okay?
Yes.
Yes. Hello, everyone. Welcome to Sustainable Horizons webinar series. My name is Yaqing Shu, the managing editor of Sustainable Horizons. I'm thrilled to be your host for today's presentation. Before the presentation, please allow me to introduce today's speaker, Professor Michel Boufadel. Professor Boufadel is a distinguished professor of environmental engineering and director of the Center for Natural Resources. Professor Boufadel also serves as the chief editor of the Marine Pollution Bulletin and an editor for Sustainable Horizons. He is a professional engineer, a board-certified environmental engineer, a professional hydrologist, and a fellow of the American Society of Civil Engineers. He served recently on 6 National Research Council committees in relation to environmental issues. Professor Bouffadel's expertise is modeling large-scale environmental systems, floodplain delineation, coastal systems, and environmental fluid mechanics. Today, we also have many audience on Zoom. Meanwhile, there are more people joining us on the WeChat platform. If you have any questions, we can address the question by the end. For the audience on Zoom, you can raise your hand. For other audience on WeChat platform, you can leave your message in WeChat chat box. Okay, then let's start. Michelle, over to you. Now you can share your screen.
Okay. Thank you, Dr. Shu. Let me share my screen. Okay, and then. Okay. So I will talk today about, two related issues. As Dr. Shu explained, I mean, my other hat is the work on fluid mechanics. We do stormwater delineation, investigate the mixing of multi-phase behavior, especially in relation to oil spill. But about 5 years ago, I started working on this topic of resilience. And some of it is, you see from the talk today that some of it is like just basic hydrology, you could call it. But the other one is at the interface between engineering and hydrology and, maybe social sciences. So social science. Okay, so let's talk about climate change. And the idea is really what we know. If you look at this is an area mid-Atlantic, New York area, New York City area, and it is expected, there are measurements up to 2005, and then the rest. These are models that are predicting. This is predicting the anomaly, and depending on the scenario, you could have an increase by the year 2100, you could have an increase of like maybe 3 degrees C or up to 7 degrees C. It depends on the intervention that we do as a society, and also it depends on the models. So I want to just put that out, that these models, they already run, and the data are available for people to use. So they give you a lot of data, these models. So these models, they are known as global circulation models. And I think now there are 41 of them. And they solve for the whole hydrodynamic equation around the globe. And they give you the air temperature, wind speed, precipitation, at different, at the time scale, usually of like day or 6 hours. And sometimes, so 6 hours to a day. So these data that you see them, they could be available, daily or even every 6 hours. Now, the challenge with using these models is that they give you the data at a very large scale. And, so the grid could be 200 kilometers by 200 kilometers. Now they're getting smaller and smaller, which is great. But nevertheless, our approach now is you want to use the data from these models. So you want to use, the models predict all of, the table that you saw before at the given nodes, and then you need to try to use these data to predict at a given location, let's say in the New York area. There are two approaches to go from the large scale to small scale. One is called dynamic approach, which I will not discuss here. And the other one is statistical, which is kind of empirical. The advantage is that it's easy to do, it's easy to consider different scenarios, and that's what we pursued. Now, again, the goal here is not to get into the downscaling details. We use machine learning. I had a student, Firas Georges, who got his PhD from computer science, and he developed a method called AIG, attention-based input grouping. And these are illustrations that how you can, take the predicted and then compare to the observed. And in general, he was able to produce this behavior for multiple data sets. So this is, the idea is the downscaling needs to happen. Now, one could spend a lot of energy explaining these techniques, and I feel that it's not relevant for this audience. One thing with downscaling, like this is an illustration about wind speed, is just to pay attention to the uncertainty. Okay, so in this particular case, you have the observed data, these are the dashed lines, and then you have, what we predicted. And then there's also the uncertainty, whether the uncertainty is due to the data, aleatoric, or epistemic, which is due to the model itself. Nevertheless, what we are simply saying here is that, okay, you wanna downscale, but you wanna pay attention to the uncertainty. Now let's try to get more into some of the challenges. There's something known as urban heat island. Cities experience higher temperature than surrounding areas. But there's a challenge in trying to predict or understand, the urban heat island, the UHI. So it, for a simple system, it's not that difficult. I mean, you can just look at surface reflectance, the albedo, the color of the surface, and then, you may conclude, based on simple energy configuration that which one is going to retain more, more heat than another. But as you know, in these systems, in cities, you have multiple floors, multiple stories, you have different usages. So it is really, the issue is an issue of quantification and not the lack of the science. In essence, how to quantify it accurately. And if you decide to take action, what can you do to mitigate, to reduce the urban heat island? So this is the area here, we're working on. We are in this, my university is city of Newark, and you probably heard Newark Airport, and this is New York City here. Okay, so we are like, half an hour, 20 minutes from New York City. This is New York City. This is, the town where NJIT is located, my university, New Jersey Institute of Technology. So when you look at the city of Newark, this is July 12, 2018, you can see the temperature, some places is 36 degrees C. The other places could be, 14, maybe this is water, but regardless, there's like 5-6 degrees centigrade difference between different locations. And the goal is that, what to do about it. Now, what we know that urban heat island causes, severe health episodes, especially for, vulnerable population, elderly people maybe who are overweight, but also, children. So there's that aspect of it. Also, urban heat island combines with, poor air quality to make things even worse. So the concern about urban heat island is really it's about public health rather than just a level of comfort. There are approaches to use machine learning techniques for urban heat island, and most of them they require that really using data obtained by ground sensors. Our approach, working with the folks at Princeton, Dr. Firas Gergis, who is now at Princeton, to use satellite images and to obtain these first to kind of predict the urban heat island, and then if you decide to take some action, how can you reduce the urban heat island? There is a good data, satellite is known as Landsat. It provides high resolution over the US, 30 meter. It is cost effective, and it gives you a lot of data, as you can see here, different bands, different colors. In this, and that it gives you data every 2 weeks, for a given location. From this one, we use only band 10, and there are other ones you will see we use different source. The RGB, red, green, and blue, we use from different source. So we use band 10 from this 100-meter resolution thermal mapping. This is the the image you saw earlier, and estimated soil moisture. So the approach is we use another satellite from the USDA. It's called NAIP. And that one doesn't have the same temporal resolution, but it gives a high spatial resolution at the 1 meter scale. And then it gives you for the RGB. These are the basic element of colors. But we also use the LSAT to obtain land surface temperature, and then also the effect of the cloud. And here it's an illustration how the cloud impact is removed. So if you look at something here, and then you can get it here, so you can remove it, and then the basic concept here is to combine between this information and then the thermal imaging, and then essentially think of it like as correlation. What we know is green areas, green roofs, reflective surfaces, they reduce the urban heat island. So we are just trying to find that relation at that scale. And then if a city decides, which now we're working with the city of Newark, they're gonna plant about 1,500 trees. And we're working with them on that. So, okay, once, where to plant the trees to maximize the reduction of urban heat island. This is the methodology that done by Dr. Gergis at Princeton, and I mean I'm not gonna go over it, but it uses LULC, land cover data, and along with the satellite imagery to obtain the land surface temperature. So the deliverable in a summary. So this is what we are hoping to get. We're hoping to get a basic approach that could, is not, maybe highly accurate, but it is accurate enough for decision making to reduce the urban heat island based on policy decisions, such as planting trees, converting, to green roofs, or painting the roofs white, or any other action. Okay, now this is the second part of my talk. Let me just check. Okay, we're good. So we know that climate change will increase the rate and severity of storms and droughts. Okay, so I just put that out there for us to kind of like realize what is the main thing in terms of urban environment, that you're gonna have events where you have a lot of rain, but then between these rain events it's gonna be very dry, so you could have drought. And this is in our region here in the New York area. That's the prediction. In different regions, it might be it might be the opposite. Maybe if you go up further north, it could get more humid. So that's something else. Now, one of the things is resilience, and this is a concept came from biology and social science. Resilience is the ability to prepare for and to recover following a disruptive event. And there are many, definitions that are related to this one. But the main thing is that, how to recover following a disruptive event. If a system recovers fast, then, you might say it is resilient. If it recovers and reaches back certain level, you say maybe it hasn't recovered fully. So based on this, in the US, there are indices to predict when a system is resilient. There are various ones. This one here, I will talk about the CDC SVI. This is social vulnerability index is used in many places. So, and this is the next slide talks more about it. So it's adopted by the CDC, Center for Disease Control in the US. It quantified the vulnerability of a community to disaster. Notice it's vulnerability, not resilience, but it's highly used. It relies on how the community weave is made, how much the transportation is available, the housing, the connectivity. So it has many elements to kind of predict, or at least to give an index about resilience. For us, we say all of these indices, they are not sufficient because these are pre-disaster metrics. These, where in reality, the resilience should, it will depend on the stress level. So a case in point, imagine that you have a functionality. Think of this as square miles of roads available, okay? Think of this as a number of hospital beds. And any, the power available, electric power that delivered, and then you have a disaster, and then it drops. Okay, imagine 50-year, 50-year event. So, and then it drops, and then maybe it recovers. So you say, okay, this system is resilient to a 50-year storm. Well, for a 100-year storm, you expect the drop in functionality to be larger in general. And then it might take longer to recover. It might recover directly upward, but regardless that, the dip is lower. And, if you have a 500-year event, the system might not recover. Therefore, using pre-disaster, indices might not be sufficient. One needs to account for the stress level. So what we believe is one should compute the actual resilience. And the actual resilience is you start with the functionality of something, as we just talked about. Let's say, number of available, number of cars, average daily traffic. And then, you can track what happened following a disaster. By definition, from engineering concept, resilience is the area under the curve. That's it. So it is the area under the curve. Okay. So you could integrate it. You could assume, straight line behavior for simplicity. You do have to decide over what time scale you would consider a system resilient. So because it depends on the system. If you have an area, let's say like Qingdao or New Jersey, you might say, look, I care that if there's a hurricane or something, I want this to recover within maybe a month, maybe 3 months. You wouldn't say I want the next day to be everything to be open. So the time T, large T, it depends on the system. If you're dealing with the power network, electrical, power, your duration T might be 5 hours, 6 hours. Nevertheless, we are just using this approach. We are moving away from the indices to actually computing the resilience itself. One could also go into multiple dimensions. You could that one you have 1D. You could deal with what you call resourcefulness, and then you can also deal with redundancy. These are all elements of resilience. But I think for our purpose, I think we could, and for tonight, and for the work that we already have done, we're gonna just think of integration under one line, the area under the curve. So what we did, we combined, for an area, we call it, area resilience. That's the resilience metric for an area, not for community, because sometimes the community itself moves. Following Hurricane Katrina in the U.S., New Orleans, there were many people who never returned. But all the decisions were made based on the region of New Orleans. So that's why we think resilience is more an areal or regional parameter rather than related to community, as many of the previous indices they are considering. So in the areas, we have energy, health, natural systems, socioeconomic, and transportation. We just selected based on discussion with a variety of researchers. This is still work in progress, so we are actually going to update it. Like socioeconomic, there are factors that you can consider. Number of people with college degree. Well, the higher you have, the more resilient the system is. You could have a creative class if people they have skills, like a carpenter. In terms of resilience, is a carpenter would make your community more resilient than someone maybe who just who's a clerk. So the more skills, what we find out is that the more skills, the more resilient the community is. The per capita income and the per capita GDP. This one gets affected by this disaster. So this one changes. Many of these, they are pre-storm events, but or pre-disaster event. This one, the GDP would change, and that will be an indicator that what's going on. You have the same thing for energy. If you have microgrids, if you have power distribution, transportation, the same thing. The road area is gonna be impacted if you have a disaster. So that's gonna affect your the resilience. So it's not only a pre-disaster index. There are metrics that are pre-disaster, but others they you have to track them through a disaster. The AADT, that's an important one. That's why we gave it a weight of 0.6, the annual average daily traffic in the community. This one, you could imagine, this is the one that dips following a disaster. Maybe the roads are closed, or maybe sometimes people, they just don't come there. But that means that the community, the region, the economy is not recovering. So this is just, you can put them together. You can track them for health, number of hospital beds, education, transportation, and then you could also consider different action for natural system. If you have a green area, flood mitigation, urban heat reduction, this is what we mentioned all. So you could link this to what we were working on in terms of urban heat island. And then what we did, we took this and then we couple it, we made it a GIS tool. And now I'm gonna click on it. And so I'm not running it now, it's just running by itself as an animation. So this is New Jersey. You take an area. This is what we did for all of New Jersey. You could highlight an area, and then it will, let me stop it here if I can. And here, these are like the various parameters, how much it dropped, how much it took, how many days. These are hypothetical scenarios, how long it took to recover for different sectors. And so you obtain this information. This is after the disaster. So after the disaster, you obtain them, and then you can compute how resilient your area was. So you could, but when you integrate all of these, you could realize, okay, that my resilience score after 90 days was 7.5, which is, you say, okay, it's pretty good. Maybe someone say, I want to know after 60 days, and they realize that it is 2.5. So in that regard, so not only we integrate resilience, or we compute the resilience score, we also integrate it over time. So decision makers can make decisions, at what moment intervention should be made. And some of these, they have to, like in the US especially, they have to do some time with the federal government bringing resources into that area. And then also it can go, you can select by municipality, but I'm gonna skip that. So you could compute also, the question is, okay, so this is for previous events. How about future events? Well, future events, one needs to consider different scenarios in the Monte Carlo simulation approach in terms of, say the flood level. And what we're working on is how about decision made by community? We are using an approach is known as agent-based modeling, to reproduce the decision of communities. And so that will allow us to actually predict what will be the resilience score for various communities, for various areas. And that's my last slide. Thank you.
Okay. Thank you, Professor Boufadel, for your interesting presentation. Climate change and urban resilience evaluation are always important research in recent years. Professor Boufadel introduced the method of downscale climate models and to better predict urban heat island and stormwater. They use information from 5 sectors, including economics, energy, healthy, natural systems, and transportation to compute the resilience of regions at various scales. In addition, we also learn a lot about how to use refined climate models to quantify assess water and food security. Very interesting. Thank you very much. And does anyone have questions? Or I will start with my own question. You know that there are many mega cities in China with a population of more than 10 million or even more, even doubled. In the past 2 years, there are some heavy storms have brought great challenges to these cities, including serious people death and property loss. Maybe you know from news, some news about this. So based on your research, what kind of advices you can offer to these mega cities?
Yeah, I think, well, I mean, there are different levels. If I may mention, like, the issue with the urban heat island, I think that's very challenging in the sense that, I mean, I'm a hydrologist, I'm an environmental engineer, and I know that we cannot predict the urban heat island location based on what do you call it, first principles. So that's the first thing, so similarly, when you talk about air quality at the kilometer scale, at the 500-meter scale, it's very difficult to predict it based, on sophisticated hydrodynamic models. So I think that's something that to pay attention to in terms of urban heat island and air quality. I think I've read a lot of good papers written by Chinese about in terms of the the downscaling. So I think that's great. I feel that this issue of resilience, what we presented here, mathematically is not really that complicated. But I think I'm hoping that the science community embraces it more, because we have been in many communities, many groups, you hear talking about people talking about like how to make a particular city resilient, and then you find that okay, they build a seawall, or they build water treatment plant, and to me that's maybe make it more robust, or more resourceful. I think we need to adopt this aspect, or this definition. It's not the definition of resilience. This is actually the concept has existed in engineering. It's just that we as engineers and scientists, we never paid attention to it, that it is some an integration of something, and I think this is what would bring different scientists together, because it is really integrating the role of different different what do you call it, sectors. So so in my assessment, it is the notion of resilience can bring advancement to cities, and definitely to urban areas.
Okay. And another question related to the parameter you used in Iris model. I saw the perfect score and also the contribute weight you used in the model. How do you balance? Are these what do you think? Are these objective or subjective? Sometimes you need to balance this two in the model, right?
That's an excellent question. I think that's from a pure scientific point of view, the perfect score is always a challenge. Okay, but we believe that we need to start talking about first intrinsic resilience. So but it depends on the region. So this is for the Northeast. This is New Jersey, New York, Philadelphia, Boston. This is what we believe is the Northeast. If you go inland in the US, if you go to Europe, to China, I think they're going to be different values. That's for sure. So it depends on the region, the perfect score. But I believe, and my colleagues too, that we need to adopt a perfect score. So not everything is comparative, because what has been happening in the US, for example, they go and rank, take a state and rank the counties, and then they conclude that this is the most resilient, this is the least resilient. But maybe the most resilient is not resilient enough. So we need to kind of try to have some intrinsic or absolute value of resilience. That's one. The weights, that's another challenge. It depends on the region, and that one, I think it is more nebulous. We just got funding to conduct what they call a Delphi survey, essentially the survey of the experts. So that is, yes, the weights, how to assign weights, it is really challenging, but we think that the goal is to say, look, is the era's value, is it 8 or 3? I'm hoping like it's not going to be 8 or 6.9. I mean, if it is that range, you cannot make major decisions. I feel like the weights, they would, if they are so-called reasonable, well-behaved, as the mathematicians use, I think we would, the eras would just tell you if a region, if resilient or not. But it's not going to tell you if it is very resilient or super very, very resilient.
Yes, I really agree with you. And I also read the paper you published on Sustainable Horizons. You indicate that the weight and may be different for different regions, and maybe also it will change over the time.
Yes, and then
Yeah.
what we are thinking, because now, and this is what I talked with Dr. Shumio Zhang, the editor-in-chief of Sustainable Horizon. One of the ideas what we want to pursue, and putting a special issue together, is reach out to the financial sector here in Wall Street, in New York, and through universities, through finance faculty, and try to bring that component into it. Okay, and so that's what we are working on now, to bring the what they call it, the financial sector into this, because that also determines, it has implication in terms of on the insurance, like because if a system is resilient, then it means maybe. So because currently the insurance is based on vulnerability, based on if something can break. But what we are hoping is people use resilience, so it might break a little bit, but then if it can recover, then it's not only the risk, so it cannot be only the risk, it's also the recovery. So we think using resilience for allocating the premium, how much you pay for the insurance, might be more realistic than just using the vulnerability and the risk and the exposure.
Yes, thank you. We have two more questions in WeChat, three more. The first one, why does resilience depend on the level of stress?
Why does it depend on the level of stress? Because from engineering systems, resilience is really how the system breaks and then how it recovers. So what we saw here is that just imagine you have a 50-year flood. It covers certain area of the town. Then you get a 100-year flood, it covers more. So of course you could have a seawall and then stop them all. Okay, but that's the ideal scenario. Usually you don't have enough resources to make the system 100% robust. You don't. So you tolerate a certain level of failure. I mean, like when they build a seawall, they say, okay, we're gonna stop. Let's pick a number, 500-year storm, which is huge. Well, imagine that after 20 years you get a 1,000-year storm. So it will always, you will never have enough resistance to make the system 100% resilient.
Yes, to simply understand something destroyed and they are destroyed, cannot be recovered. That's my understanding.
Yeah, but I think the question was like, maybe you stop it, but I'm saying if you have the resources, again, just imagine the flood. If you have the resources, like, okay, 3-meter wall, stop the 50-year flood, 5-meter wall, the 100-year flood. Okay, maybe here you need 20-meter wall around the city. And you say, look, I cannot build a 20-meter high wall around Qingdao. That's too much. So at some moment, the resources, how much money you want to spend, you say, I don't have it.
Yes.
And then you accept failure, but this is in every engineering design, we accept, there's all the probability of failure.
Yeah. The second question, has this model arrays been applied to evaluate and help to improve the resilience of any city or region in reality? How is the effect?
We are working, as we speak now with the city of Newark, the one you saw. So we are regularly meeting with them, with the sustainability office. The city of Newark has like 300,000. So yeah, I mean, it's not 10 million. like the cities you mentioned. But it is really a highly urbanized area, and we are working with them for that particular purpose. We have the funding for that, and I'm hoping within maybe a year we get the weights as you asked, Dr. Shu, and maybe we adjust some of the perfect scores. But I think the bigger issue, as you said, it is how to get the weights. And then once we do that, we say, okay, let's look at previous events. So here in New Jersey, we have Hurricane Sandy. You say, let us check, so we go and do retrospective studies to see how areas, what would be the score. And so that's how you would validate such a model, by getting the input of the experts and by trying to measure previous disasters and then see what happened. So I'll give you an example. Like for Hurricane Sandy, let's say the whole region was devastated for 6 months. Imagine now we plug in areas with the weights, and then we found that the area recovered in 2 months. Then we realized that the weights are wrong. So it has to reproduce whatever is subjective. I mean, there's a degree of subjectivity, but I think that's what stopped many people who are quantitative from working on this. And I think we should accept to work on this with uncertainty.
Yes. And the third question, why is resilience related to the transportation infrastructure?
In essence, the flooding, if you have, if an area is flooded, okay, I mean, there are two levels. One is, sometimes people imagine, okay, that there's a flooding and there's the bridge that got destroyed, or there's the road. Okay, that's like a real major issue, okay? But I think sometimes it's just, imagine the roads being blocked, this just flooded. To me, the resilience, when you think of an area, you say, the return to normalcy. It means, do people go to school? Do people, go to their work? Are the trucks driving, delivering goods? So in that regard, transportation, if it is not functioning, that is telling us that the system has not returned to normalcy. And then and these, like for example, this number AADT. Well, one is you could count after the disaster. You could count how many trucks you get there, how many cars, and then you say, okay, it means that reproduces the level of a GDP, but also it is also here. We are also computing the GDP of that area, but it cannot be one parameter. This is the challenge for resilience of an area. You need more than one parameter to capture it, because let's say the GDP, you have everything shut down, and then you have a major factory producing, goods and then selling, making chips and making a lot of money. So the GDP is the same. You say, we're fine, but no, that's not the same. We need to include, there are other factors here we are including, such as employment or unemployment, percentage. But so you need all of these indications to say, did it return to normal?
Yes, as I understand, more factors considered in the model and better maybe the accuracy, right?
Yes, yeah. I mean, the accuracy for a lifestyle. I mean, like, during COVID, we were all of us stuck at home, all of us, at every place. It's like, okay, is that what we want to do for the next 20 years? So I think it's more of as a society, what do we want to do? I mean, so I mentioned COVID, but again, hurricane, heat wave, the same thing.
Yeah, transportation also always is a very important factor as the operation unit of the city system.
Yes, I mean, for us, New Jersey, it is a big deal also, because we have there's something called New Jersey Turnpike. That's the major highway. It takes things from Washington, D.C. all the way to Boston. That's the major hub highway. And then you have, we have a port of Newark. This is the third largest in the U.S. So transportation for this state, New Jersey, is very important. There's also the Newark airport. Some states, maybe Montana, maybe transportation is not a major issue as much as production of, agriculture. So there are ways to adjust things.
Yeah, thank you.
You're welcome.
If there's no more question, we will close the webinar for today. And for the audience, if you are interested in this topic, I think you can find more answers in the paper, right? Published on Sustainable Horizons.
Yes. Sustainable Horizon, you find me, we're going to have special issues. But anyway, looking forward to working with the whole community of Sustainable Horizon. Thank you, Dr. Shu, and everyone. Yeah, thank you. Once again, many thanks to Professor Boufadel for the interesting presentation. Thank you all for joining. Bye-bye.